Offline reinforcement learning has shown great potential in many robotic tasks. However, it is still challenging for long-horizon tasks with suboptimal and multimodal offline datasets. Existing works rarely consider the structured information in offline datasets, which is commonly found in many robotic tasks and useful for addressing the above challenges. For suboptimality, datasets collected can have significant suboptimality. For example, the robot uses the hammer to hit the top of the nail, or the bottom of the nail. And some trajectories miss hammering the nail. For multimodality, datasets collected can consist of different solution trajectories. For example, in the kitchen task, only a subset of the desired tasks in each trajectory is completed. The three trajectories complete different subtasks respectively. In our method, we first decompose the long-horizon difficult task into short and simple subtasks and build the task graph based on the offline dataset. By finding the optimal subtask sequence to the target state, we then use the task graph to sample and generate an augmented dataset, which is more suitable for offline policy learning. After that, we relabel the dataset according to the task graph and finally learn offline reinforcement learning policy to complete the long-horizon task. We first evaluate our method on two dexterous manipulation tasks. One task is to control the anthropomorphic hand opening the door. With only 25 suboptimal human demonstration trajectories, our method substantially outperformed all the compared methods. BCQ couldn't do anything, Iris could reach the door, and our method could open the door. We can see that our method in turn completes reaching the handle, turning the handle, and opening the door. Another task is to hammer a nail. BCQ couldn't pick up the hammer, Iris could only pick up the hammer, and our method could successfully hammer the nail. Benefiting from the guidance of the subtask and dataset augmentation, our method will first complete the subtask of picking up the hammer and then hammering the nail. In the kitchen partial task, the target task is to open the microwave, move the kettle, turn overhead light on, and slide open the cabinet door, as listed in the box. Our method could complete the whole task in order, while the others could only partially complete the task. With the subtask relabel and dataset augmentation, we can find the optimal subtask sequence to complete the subtask one by one and learn a stable offline policy. In the kitchen mixed task, the target task is to open the microwave, move the kettle, open the bottom burner, and turn overhead light on, as listed in the box. Our method could complete the whole task in order, while the others could only finish several subtasks. We conducted an evaluation of our approach on a complex, long-horizon, real-world manipulation task. We use a 7DoF Canova Gen 3 robotic arm equipped with a robotic gripper. The task is to build a ladder with 3 different blocks. Initially, these blocks are spread out on the table and our goal is to align them to build the desired shape. We utilized a rule-based policy written by hands to collect 6 different types of trajectories. One type of trajectories precisely completes our target task, building the ladder. However, the other 5 types of trajectories either partially achieve the target task or misplace some blocks, acting as potential distractions from the target task. For each trajectory type, we gathered 20 trajectories, for a total of 120 trajectories. By doing so, the collected dataset contains multimodal trajectories with suboptimal and narrow data distribution, which is very challenging for offline RL. We conduct offline training for all methods with the same datasets and then test the trained policies in the real-world robotic manipulation task. CQL encounters severe extrapolation errors, rendering it unable to pick up any blocks. IQL could place one block in the right place but will quickly knock over it, which results in an OOD state and the robot have no idea what to do after that. Relying solely on dataset mimicking, BC misplaces some blocks due to the high multimodality of the dataset, which results in a low average return. BCQ, WGCSL and Iris only partially complete the target task, which may be caused by the inaccurate value estimation of the long-horizon task. By utilizing the task graph, our method decomposes the target task into 3 subtasks and could successfully complete them in order. After 50 epochs offline training, our method can place 1 block. After 200 epochs, our method can place 2 blocks. After offline training for 1000 epochs, our method can successfully build the ladder. The results confirm that our method with dataset augmentation and subtask relabel is really effective in real-world long-horizon robotic tasks. Thanks for watching.